Here is on how to obtain the single moment equation of the beam we have solved from the double integration method. Just like what we did on our previous example, we will follow some simple steps in order to obtain the single moment equation of the beam. The first step is to solve the support reactions. Second step is to select a reference point where we will obtain the single moment equation. The third step is to pass a cutting plane on the segment which is located farthest from our selected reference point. On the fourth step, we will obtain the single moment equation using the left part of the cutting plane as our free body diagram. Then finally, we can graph the bending moment diagram of the beam using the single moment equation that we obtained. We will now start in step number 1. We solve for the support reactions. Before we will apply the equations of static equilibrium, we will solve first for the resultant, and it is just equal to the area of the load. Since the intensity is 20 kN per meter and it is applied in a length of 4 meters, that is from point C up to point B, the area is equal to 20, the intensity multiplied by the length where it is applied, that is equal to 80 kN. It is located at the centroid of the length where it is applied. Since that is 4 meters, half of 4 meters will be 2 meters. From point C and point B of the beam respectively was the location of the resultant force. We will now apply summation forces along vertical is equal to 0. We will assume that upward forces are positive. AY was assumed to be upward, that is positive, and the resultant force is downward, so that is negative in our equation. So from this equation, we can be able to solve for AY, that is equal to 80 kN. Our assumption that AY was an upward reaction was correct, since 80 kN came out to be positive. We will apply summation moment at point A. In order to solve for the moment reaction at point A, we know that the resultant is located 4 meters from point A, that is the moment arm. Since from point C up to the location of the resultant is 2 meters and A to C is another 2 meters. 2 meters plus another 2 meters is equal to 4 meters. Our assumption in applying summation moment A is equal to 0 is clockwise moment positive. On the first term of our equation, we have 80, the resultant, multiplied by the moment arm, that is 4 meters, is positive with respect to point A, since that is a clockwise moment with respect to point A. MA, the moment reaction at point A, is negative since that is a counterclockwise moment with respect to point A. So from this equation, we can be able to solve for MA, and that is equal to 320 kN meter. 320 kN meter came out to be positive, so our assumption that MA is a counterclockwise moment at point A was correct. Just like what we did on our previous example, we will again select a reference point where we can obtain the single moment equation. Like we have frequently reminded, the left end of the beam was selected the most using other references like textbook and reviewers. To avoid confusion, I will also select point A as my reference point in obtaining the single moment equation of the beam. We move on step number 3. We will now identify where will be the segment which is farthest from our reference point. But before we can do that, we have to count first how many segments does the load divide the beam into. The beam will be divided into segments if the beam is subjected by a concentrated load, partial uniformly distributed load, and partial varying load. Since our current example is subjected to partial uniformly distributed load, the beam will be divided into segments, that is segment AC and segment BC. Simply means that the graph of the bending moment diagram from point A up to point C is different on the bending diagram from C to B of the beam. As we can observe, here is the bending moment diagram of the beam. To those who are familiar with the bending moment diagram, we know that from point A to C, it consists of a first degree curve, and for C to B, that is a second degree curve due to the uniformly distributed load. Those two curves of the bending moment diagram will be defined by different moment equation. What we need is a single moment equation that will define the curve or the graph of the bending moment diagram from point A up to point B of the beam, and that is what we call the single moment equation. We will now pass cutting plane that will cut the segment which is farthest from our reference point. We have only two segments, that is AC and BC. The segment which is farthest from reference point A is segment BC. Here is now our cutting plane, that is cutting plane A-A. We select the left part of the cutting plane as our free body diagram to obtain the single moment equation. The distance from point A up to the location of cutting plane is arbitrary, that is x. Here is now our free body diagram after selecting the left part of the cutting plane as our FBD. We will now solve for the other distances in terms of x. Since the distance from point A up to the cutting plane is x, and the distance from A to point C is 2 meters, then the distance from point C up to the cutting plane is equal to x minus 2. The resultant portion of the uniformly distributed load is equal to the area, and that is equal to the intensity multiplied by the length where it is applied. So that is equal to 20 multiplied by x minus 2. Since resultant is located at centroid, the length is equal to x minus 2. Therefore, it is located at a distance of x minus 2 all over 2 from the cutting plane. After solving for the forces and distances in terms of x, we can now obtain the single moment equation. So on the first term of the equation, we have 80 kilonewton, that is force multiplied by distance, which is equal to x, that is 80 multiplied by x. And for the second term of the equation, the force is equal to 20 multiplied by x minus 2 multiplied by its moment arm, that is x minus 2 all over 2. And on the third term of the equation, we have 320 kilonewton meter. Since 320 kilonewton meter was already a moment, there's no need to multiply it with the distance. If we now multiply x minus 2 into x minus 2, that is equal to x minus 2 squared, then if we further simplify, that is now equal to 80 multiplied by x, then 20 over 2 is equal to 10 multiplied by x minus 2 squared minus 320. We will now determine the sign convention. Since 80 kilonewton will concave the beam upward with respect to the cutting plane, then therefore that is a positive moment. Since 20 multiplied by x minus the resultant of the uniformly distributed load will concave the beam downward with respect to the cutting plane, that is a negative moment equation. And since 320 kilonewton meter will concave the beam downward with respect to the cutting plane, moment will be negative. We can now observe that 80 multiplied by x is positive since it will concave the beam upward. Then the second term of the equation, 20 multiplied by x minus 2 multiplied by its moment arm x minus 2 all over 2 is negative since it will concave the beam downward. 320 kilonewton meter concentrated moment at point A, it will also concave the beam downward, so that is a negative moment. We can now observe that our equation will be valid throughout the length of the beam if we neglect the term of the equation 10 multiplied by x minus 2 squared for x values less than 2 meters. We can clearly understand this if we focus our attention to the cutting plane and think that it is moving from left to right. We know that if the cutting plane is located from point A up to point C, that is at x is less than 2 meters, here is the free body diagram, and we can observe that the uniformly distributed load will not be included to the free body diagram, and thus it will not contribute moment into the beam. As a reminder of this restriction, our mentors in engineering adopt a notation in which the usual form of parenthesis is replaced by pointed bracket. So we will now replace the usual parenthesis with a pointed bracket. With this change in notation, we will obtain the single moment equation that defines the curve of moment diagram throughout the length of the beam. We should always remember that every time we perform the operation inside the pointed bracket and it will yield the negative answer, then the term consisting the pointed bracket will not exist. If we will now assume values of x with increment of 0.5 meters, we can obtain the corresponding values of moment. That if we connect together, the graph of the bending moment diagram will be constructed. If we assume x is equal to 0, we just substitute the value of x is equal to 0 in all the terms of the equation containing x in our equation. Since 0 minus 2 is a negative number, the second term of the equation will not exist. 8 multiplied by 0 is 0, therefore m is equal to negative 320 kilonewton meter. At x is equal to 0.5, we substitute the value of x is equal to 0.5 in all the terms of the equation. Since 0.5 minus 2 is negative 1.5, the second term of the equation will not again exist. At x is equal to 1 meter, x is equal to 1.5 meters, using the same argument, the second term of the equation will not exist. We can solve for the corresponding values of m, that is equal to negative 240, 200, and negative 160 kilonewton meter respectively. At x is equal to 2.5 meters, we can observe that 2.5 minus 2 is a positive number. Therefore, the second term of the equation will exist at x is equal to 2.5 meters or x is greater than 2 meters. If we now calculate the values of corresponding m, that is equal to this value, that is negative 122.5 for x is equal to 2.5 meters. At x is equal to 3 meters, that is negative 90 kilonewton meter. At x is equal to 3.5, negative 62.5. At x is 4 meters, that is negative 40 kilonewton meter. At x is equal to 4.5, that is 22.5 kilonewton meter. At x is equal to 5 meters, that is negative 10 kilonewton meter. And at x is equal to 5.5 meters, that is equal to negative 2.5 kilonewton meter. At x is equal to 6 meters, m is equal to 0. From that data, we can be able to graph the bending moment diagram of the beam. So here is now the bending moment diagram. Even if from point A up to point C of the beam, the graph of the bending moment diagram is a first degree curve or a straight line, it is defined by the single moment equation. This is equal to what we have obtained. And from point C up to point B of the beam, we have a second degree curve, and still the single moment equation will define that curve. Here is now the single moment equation that we need in order to solve the slope and deflection of this beam using the double integration method. I hope that you have learned a lot from this example. To those who want a copy of this file in PDF, like and subscribe, comment down your email below, and I will send it to you. Thank you.